Look at energy, there's kind of a few things that we really need to touch on. That's that there are two different types of energy, and then numerous different forms of energy on top of that. And the different forms of energy can be one of the types or the other type of energy. Some forms of energy can be both types of energy at the same time or independent of each other. Some forms of energy can only be one type. So just a bunch of stuff to get into. So let's jump right into it. So the first kind of question we have to address, like, what is energy, what are the types, and then how does energy change from one form to another, which will be addressed. That last question will be addressed on a separate video. But so energy itself is just the ability to do work. And we kind of get this. We have a very specific definition of work, which we'll get to later in the year. But we just need to know that energy is the ability to get things done, to do work. And there's two types. Energy can be either kinetic, which is the energy of motion, or it can be potential, which is energy that is stored up for use at a later time. It's not currently being used to do any work if it's potential energy. Kinetic energy, because it's energy of movement, is currently being used to do work. So there's this law of conservation of energy, and we're going to run into a lot of these laws of conservations of things, but they pretty much all follow the same format, and this is that in the case of law of conservation of energy, it's that energy cannot be created or destroyed, but it can be transformed or converted from one form to another. This means that energy is never lost, never created, never made. All the energy that we have in the universe, we have the same amount of energy right now that we had, millions of years ago, and millions of years from now we'll still have that same amount of energy. You can just change forms, change locations, but within the universe as a whole, which you can call a closed system, the energy remains the same. The whole law of conservation of energy ties back into a closed system. So this is a closed system is a system where there is no way for energy to get from outside of the system in, or from inside of the system out. It's sealed off in that respect. It's also important to consider the fact that anytime energy changes its form from one form to another form, there's going to be some friction, and this friction causes some of the energy that's being transformed to be converted into thermal energy or heat. And if we think about like machines are things that convert energy from one form to another. When you have a lot of friction, these machines get hot. This means that a lot of the energy that's going in, like say it's a car and I'm putting gasoline in. Gasoline is my form of energy that's going in. There's a lot of friction. A lot of the gasoline is being used and converted over. The energy from that gasoline is being used to produce heat rather than produce the motion of making the car go forward. We say that this makes the machine less efficient. Really, the goal is always to have machines that are very, very efficient. So we want to minimize the friction in machines, or when we go through a energy conversion. So there's a couple different types of energy, as I mentioned. There's potential and kinetic energy. So potential energy, this is energy that's stored, and the one type of potential energy we'll focus on most in terms of what considered mechanical energy, which we'll talk about in a couple minutes, is called gravitational potential energy. And this is the energy that an object has due to its position and its shape or size. So, like the higher something gets up, the more gravitational potential energy it has, or the more that it weighs, the more gravitational potential energy that it has. So we can actually calculate this as gravitational potential energy is equal to the weight of an object multiplied by the height of that object. That's a way we can actually calculate this. And then there's kinetic energy, and again, as stated before, this is the energy of movement or motion, and it depends on the mass of an object and the velocity, which is kind of like the speed and direction that the object is traveling in. In this formula, its kinetic energy is equal to the mass times the velocity squared divided by 2. So this means that velocity, if you look at the formula and see that velocity squared, it means that the velocity plays a bigger role in determining the amount of kinetic energy an object has than the mass of that object. So with this formula, it means that the faster something is moving, the more kinetic energy that it has, and the more mass something has, the more kinetic energy it has as well. So for either one of those, they have what we call a direct relationship, where an increase in one thing, like mass, is going to cause an increase in the other thing, like kinetic energy. Again, this is what we call a direct relationship. So we're going to talk about a pendulum as it relates to kinetic energy. I'm just going to put on kind of a short, quick video clip so you can kind of see what a pendulum is in case you're unaware. And a pendulum is really just it's like a ball or a weight of some sort on a string that swings back and forth. And when it goes from one side to the other, it increases in height and it gets lower as it drops toward the bottom, and it increases in height again. So that's what a pendulum is. So when we look at a pendulum and how it relates to kinetic and potential energy, what we can think about is that if this is a closed system, no energy can get in from the outside, and no energy from here can leave. It's not actually a perfectly closed system, but let's pretend for a second that it is. If this, if the weight, or in this case I'll call it a sinker, if the sinker is higher, then it means that it has more potential energy. Its weight would stay the same, but it's physically higher, and since the way we calculate gravitational potential energy is weight times height, the height increased, so that means the potential energy increased. But when a pendulum swings up, it starts to slow down. So it hits this point where it's about to turn around, and it actually stops for just kind of like the most fractional second. Nothing that we would ever like visually see, but it's slowing down as it's getting higher. This means if we look at its kinetic energy, if it's slowing down, its velocity is decreasing, and that means its kinetic energy is decreasing. The opposite also is true as it swings down toward the bottom. It speeds up, it gets faster and faster and faster as it moves toward this bottom location, so its kinetic energy increases. But while the kinetic energy is increasing, the height away from the floor is decreasing, so that means its potential energy is decreasing. So when we move from this top spot over here, we have the highest amount of potential energy and the lowest amount of kinetic energy, and then they start to shift. Potential energy decreases and kinetic energy increases more and more and more and more and more until we hit this bottom location where kinetic energy is at its greatest and potential energy is at its lowest. And then the sinker continues to swing back up the other direction, and so we again go in the opposite direction, and now kinetic energy is decreasing and potential energy is increasing, and then it changes direction and comes back down again. The whole process repeats over. So that's like a pendulum and how it relates to kinetic and potential energy, and we'll kind of look at that a bunch of times, and it shows up in lots of different things like roller coasters and all that sort of stuff. So if we're looking at a person has a big ball on top of a hill, right here it's all potential energy. The ball is not moving at all, so there's no kinetic energy. If there's no movement, there can't be any kinetic energy. But once the guy pushes the ball and it starts to roll down the hill, the potential energy starts to decrease as it gets lower, but the kinetic energy increases as the ball starts to travel faster and faster and faster. So we said there's two types of energy, kinetic and potential, but there's numerous different forms of energy. And the way that I remember this is scream in T or scream in H, which is S for sound energy, C for chemical energy, R for radiant energy, which we sometimes call light, E for electrical energy, A for atomic energy, which we sometimes call nuclear, M for mechanical energy, and then T for thermal, which we sometimes call heat. Some other people will look at it and remember, and with this acronym, which is perfectly fine, Mrs. Chen, so it's mechanical, radiant, sound, chemical, heat, electrical, nuclear, as a way to remember that. So either way is fine. I'll probably end up saying scream in H or scream in T most of the time when I'm kind of going through them. So with those different forms of energy, and those are the different forms of energy, mechanical is the total energy due to the motion of an object as well as the position of an object. So this is the kinetic energy due to a full object as well as its potential energy. So you add those two together and you get the mechanical energy of an object. Chemical energy is the energy that's stored in the bonds between atoms that make up a substance. So all substances we know are made up of atoms, and there's bonds that hold those atoms together, and stored in that bond is energy. If we can break that bond, we can release that energy. It also means that when new chemicals are created, new bonds need to be formed, and therefore some energy has to go from the environment and into the new bond that's being formed. So we're taking another form of energy and converting it into chemical energy. There's also sound energy, and this is when whenever an object vibrates, it produces a sound wave. Some we can hear, some we can't, but it essentially pushes around molecules, like air molecules and things like that, and that's energy. Sound energy is always going to be kinetic. We have thermal energy, or heat, and this is the energy due to the movement of the particles that make up matter. So if you think about like a teapot full of water, the particles are always moving, even in really small amounts. Again, not something you're going to see with your naked eye, but they're always moving, and as they move faster and faster and faster, there's more and more energy in those particles, because this is essentially just a type of kinetic energy, and the greater the velocity, or the speed at which something is moving, the more energy they have. So that would be thermal energy. So things that, when we look at substances, things that are solid have the least thermal energy, and then as those particles begin to move faster, they become a liquid, and now there's more thermal energy. And as they move faster still, they turn into a gas, and now they have even more thermal energy. So the state of matter can tell us something about how much thermal energy a substance has. There's also electrical energy. This is the energy that we as humans use most outside of like consuming food for our own energy. And this is really just the energy of moving electrons. We normally have this electricity move through a closed circuit, which is just like a series of wires that connects for electricity to flow through. And then there's radiant energy, and radiant energy is like the energy that we would consider light energy. It's also a type of wave. It's called an electromagnetic wave, and we can see certain electromagnetic waves, and we see them as light. There are other ones we can't see, things like infrared or ultraviolet. It might be things that you've heard of. So as these electromagnetic waves travel, they carry with them energy. And some types of waves, we talked about sound energy and light energy. And light energy can typically travel faster, or radiant energy can typically travel faster than sound energy can. And this is actually why we see fireworks before we hear them, because light travels faster than sound does. So it means that fireworks, we're going to see them before we hear them, because the light from them reaches us before the sound from them reaches us. The last type of energy is atomic energy, or nuclear energy, and there's two different versions of this. There's nuclear fusion and nuclear fission. Fusion comes from the word fuse, which is to combine. This is the sort of thing that happens in the sun. And you can remember that the U in fusion goes with the U in sun. So fusion happens on the sun. And this requires really, 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 really high temperatures. This is not the type of nuclear energy we generally have here on Earth. What we have on Earth, when we have like a nuclear power plant, this is nuclear fission. And this comes from splitting an atom. We take an atom, one atom, not the bonds between atoms, but one atom itself, and we split its nucleus to make two different atoms. And when that happens, there's a lot of energy stored in that nucleus that gets released. And so that's where we get, that's what happens with nuclear fission. And that's how we get nuclear energy here on Earth in the form of like a nuclear power plant. It has to be very, very controlled, or else it can become dangerous. But if it's controlled, the danger becomes a little more debatable. And so you can remember this is the split, the I from split and the I from fission overlap, so they go together. So fusion happens in the sun, fission, which is the splitting of an atom, that happens here on Earth. So those are the different types and forms of energy that we have, and these are the three that people get most commonly mistake amongst themselves. Electrical energy. Electrical energy is just the electrons from atoms. And sometimes electrons break away from atoms, and then when they flow along a wire, that's electrical energy. These two, however, the real big ones that people get confused. Nuclear energy is about the energy that's stored within the nucleus of an atom. So it's the energy that's stored like right in here in the nucleus. as opposed to the chemical energy, which is the energy stored in the bonds between different atoms. So like the bond, this like white area here that's holding this atom and this atom close together, the energy that's stored in there, that's the chemical energy. So when we release chemical energy, we don't need to break apart the atom itself, just we need to break apart this atom from this atom. And so those are our two different types, or the comparing the differences between nuclear energy and chemical energy. All right, if you have any questions, make sure you see me.